DirectX 12 Work Graph API, which came out in 2024, is a new way to handle GPU rendering. It lets shaders, programs running on the GPU, create and launch new tasks all by themselves. This means the GPU doesn't have to talk to the CPU as much. In this work, we're testing the practical performance of these work graphs. We're focusing on a common graphics problem called shader thread divergence. Branching is known to be very bad for GPU performance. Here's why. GPUs run tasks in groups called waves or warps. The problem happens when threads in the same group disagree. For example, if one thread needs to do the if part and another thread in the same group needs to do the else part. First, it runs the if path. While it's doing that, all the else threads are masked off. They just sit there and wait, doing nothing. Then it runs the else path. Now, all the if threads have to wait. This means parts of the GPU are always idle. You lose a huge amount of parallelism, and your performance can drop significantly. This is a major issue for modern rendering. For example, in deferred shading, a single small piece of the screen might need to process many different materials, which forces the GPU to do all this branching and waiting. To empirically test the performance of work graphs in a scenario involving conditional rendering, we designed a shader binning benchmark. The benchmark's objective is to quantify the performance difference between static branching, Uber shader, and dynamic dispatch, work graph, for handling divergent workloads. We defined two distinct computational workloads. Material 0, cloud, a computationally expensive workload consisting of a 100-line procedural cloud generation function. Material 1, green, a computationally trivial workload that simply writes a static color. The control implementation is a single traditional compute shader. It is dispatched once to cover the entire canvas. Inside the shader, it samples the material ID texture and uses a simple if-else branch to select the workload. The work graph implementation consists of a root node, classify pixels, and two child nodes, shade pixels 0 for cloud and shade pixels 2 for green. The classify pixels node is dispatched as the entry point. Its job is to read the material ID for each pixel and dynamically output a record to the corresponding child node. This effectively bins all pixels by material type before any heavy computation begins. We tested 4 primary distributions. In scenario A, where the 50% to 50% split was spatially coherent, large blocks of green, large blocks of cloud, the Uber shader was more than twice as fast as the work graph. In scenario A, the materials are grouped, so no intra-wave branching occurs. The Uber shader runs at full efficiency. The work graph, however, still incurs its additional overhead from rescheduling, making it significantly slower. The work graph's strength was revealed in scenario F. Here, the work graph was about 1.26 times faster than the Uber shader. In the Uber shader, every wave that contains even one cloud pixel must execute the time-consuming cloud computation. The work graph, by rescheduling, integrates the few time-consuming cloud tasks into the same dispatch, allowing the vast majority of green pixels to finish quickly. To test how performance scales with logical complexity, we increased the number of distinct cloud material types from 1 to 11. The results are dramatic. The Uber shader's performance degrades linearly as more else if statements are added to the branch, increasing from 168. AMAs to 1876, 1 emts. The work graph's performance, column B, which scales by dispatching to a larger node array, remains far more stable, increasing from 133. NIMS to only 648, 6 ments. We provides an empirical analysis of the DirectX 12 Work Graph API, demonstrating its capabilities and limitations in a practical shader binning scenario. Our research confirms that work graphs are not a universal solution for shader divergence, but rather a highly specialized tool for specific workload patterns. The key finding is that performance is a trade-off between the cost of intra-wave branching in an Uber shader and the cost of dynamic rescheduling in a work graph. An Uber shader remains more efficient when shader divergence is spatially coherent, as it avoids intra-wave branching and incurs no rescheduling overhead. A work graph provides a significant performance advantage when workloads are spatially sparse, computationally imbalanced, and logically complex. The next logical step is to benchmark a hybrid pipeline, specifically integrating a mesh node to create a fully GPU-driven rendering pipeline with entity culling.